at this clinical quiz question here. See, a 50-year-old man was brought unconscious to the casualty. His pulse is 120, BP is 160 by 140. An emergency CT revealed a hyperdense lesion with a CT value of plus 55 HU in the right basal ganglia and centrum semioval. What is the diagnosis? Of course, on the CT, you see something bright here. Now, the diagnosis in such cases can either be clinical, that is based upon this history, based upon the clinical features, based upon the imaging findings, and all this put together will give you a diagnosis, right? That is a logical way to do it. But do you know, it is also possible to make this diagnosis without knowing any of this about the history, presentation, imaging findings, nothing. But just that this one measurement value at this particular point that they've already given you here, 55 HU, can directly give you a diagnosis in this particular case. Well, this is a great utility of a measurement scale on CT scan images. And that is what is called as the Hounsfield unit scale. What is this Hounsfield unit scale, right? How it can be used for making a better diagnosis so easily. This is something that we'll discuss in this basics about the CT scan. So the walls of the CT scanner room are lined with what? Yes, they are lined with lead. But why? Right? This is something that we'll discuss in the next few minutes. Let us jump to the invention of CT scan. Remember, who invented CT? It was Sir Godfrey Hounsfield. Sir Godfrey Hounsfield, who invented CT scan. Right? He is called as the founding father of CT technology. He invented the first generation CT scanner, which was called as an EMI scanner. Not because he took a loan and built it on an EMI, but because he was working for a company which is called as the Electrical and Musical Instruments Company. Right? He was working for this company and therefore the company's name was given to his first machine. He also devised that Hounsfield unit scale, which is therefore named in his honor. It is also called CT value scale. We discussed this. He was awarded the Nobel Prize jointly along with Alan Cormack. What is CT? We have mentioned CT multiple times. What is CT? What is the CT scan? It stands for computed tomography. What is this tomography? You'll come across this tomography multiple places. PET scan, positron emission tomography, SPECT scan, single photon emission computed tomography. What is the meaning of tomography? Tomography means cross-sectional imaging. Any technique which helps us get cross-sectional images of the patient's body is called tomographic technique. Now, if we use a computer to get this data, it is called computed tomography. If we use an X-ray tube, just an X-ray tube to get this data, it is called conventional tomography. If we use a positron emitting radionuclide to get this data, it is called positron emission tomography. If we use a single photon emission, emitting radionuclide to get this data, it is called single photon emission computed tomography. So computed tomography basically uses X-rays. The computer does a lot of mathematics which is involved in image reconstruction, and the tomographic setup actually gets the tomographic data. So remember, X-rays were a discovery, but CT scan was an invention. What is the difference between a discovery and invention? Some play of words here. Discovery is accidental. We discussed how Wilhelm Röntgen accidentally discovered X-rays when the photographic plate began to shine, right? On 8th of November 1895. But CT scan was not a discovery. It was an invention. There were deliberate efforts made to develop this tomographic technique. How does a CT scan unit looks like? A CT scan department looks like this. There are two rooms. One is a CT scan equipment room. The other one is the console room. This is where all the console is. This is where the technician will sit and plan the CT scan. This is where radiologists like me, right, will sit and report the CT scans, right, where the actual scanning takes place in the equipment room. We look at the machine in detail. Around the equipment room, there is always, in all the walls, everywhere around it, there is lead. Why is there lead? The purpose of putting up lead there is to prevent leakage of radiation, because CT scan has a lot of radiation exposure. That radiation exposure occurring to the patient is justified because there is an indication to do CT scan. Will it be justified if all the technicians and radiologists are also exposed? No. Will it be justified if the relatives waiting outside are exposed? No. Right? And therefore, to prevent this leakage of radiation, to prevent the radiation coming out of this room, right, this lead is used. How much of lead is used? Remember, a lead sheet of 1/16 inch thickness. So a lead sheet of 1/16 inch thickness, or around 4 to 6 inches of standard density concrete wall is usually considered to be enough. If lead sheet is not available, 4 to 6 inches of standard density concrete can be used. There is a glass window, right, between the console room and the equipment room through which the radiologist and technician can see the machine. This glass is also a lead containing glass, so that through this glass also the leakage of radiation should not take place. That is how the lead is used for radiation protection, to prevent the leakage of radiation out of the equipment room. Okay, now how does a CT scan machine look like? A CT scan machine looks like this. Now see, this round area of the CT scan machine, this is called as the gantry. What is there inside the gantry, we will see in the animated part. And this is the CT scan machine table on which the patient is going to lie. This table will slide inside, and that is how the CT scan will be done. Now, what is the basic principle of a CT scan? The basic principle of CT scan states that the internal structure of an object can be reconstructed from multiple projections of that particular object. Does it make any sense to you right now? I'm sure this big line, whatever I've read out and underlined here, does not make any sense to you right now. But that's okay, because now we are going to jump into the CT scan animation. And in this animation, you'll very beautifully understand what this sentence actually means and what is the basic principle of CT scan. Now, how does a CT scan machine actually work? See, this is how a CT machine looks like. We have seen, right? So it consists of a gantry and a table, and a patient whose CT scan is to be done is lying on the table of the CT scan machine. Now this table gradually slides into the bore of the CT scan machine, and that is when a CT scan actually begins. Now just imagine now that this patient has gone inside this particular gantry. What happens inside now? See, so let us open up the gantry, CT scan gantry, and let us see what happens, what is there inside it. Now inside the particular machine, on one side you will find that there is an X-ray tube, and on the other side, right, you have the X-ray detector. So we are looking at it from the front end face, right? So on one side you have an X-ray tube, the other side you have X-ray detectors. What is the function of the X-ray tube? The function of the X-ray tube is to produce an X-ray beam. So can you see an X-ray beam is being produced, and this X-ray beam is passing through the patient's body. So it is going to create a radiographic image of the patient's body, and this image is going to be detected or captured by the detectors, isn't it? But these detectors, remember, these are electronic detectors. So the data that they have collected is given a name. It is called as the first projection. This is electronic data. Now all this data which is collected by these detectors as the first projection, right, is then transmitted to a computer. Do you remember two parts of the machine? One is computer, one is tomographic setup. That is what CT scan is. So this data is then transmitted to a computer. This is just like taking one X-ray projection or one, X-ray spot radiograph that we have seen, isn't it? This is just one projection which is going to be which has been obtained here. Next, what happens inside the CT scan machine before the final image is generated is this. See now what happens. The X-ray tube now moves on to the next position, new position. The detectors are also moved to a diametrically opposite new position. Again, an X-ray beam is produced. It passes through the patient's body. Another image is created. Do you realize that this is called a second projection, and second projection is going to be different in appearance from the first projection because it has been taken from a different angle around the patient's body. The second projection data is also transmitted to the computer. This process is repeated. The X-ray tube comes at a new position, right? Again, now the third projection is obtained, again new position. This process is repeated until n number of projections from different angles around the patient's body are obtained. All this data is fed to the computer. As I said, now what the computer does at the end, when all the n number of projections are obtained, the entire data is now processed together, right? And from this projection data, the computer is going to create a cross-sectional image of the patient's body, which is going to be displayed on the screen of the computer, right? Now, if you look carefully at this particular image, suppose that we are trying to scan the chest part of the patient's body. What can you see in this image? Can you see that in this CT scan chest image, I can actually see the chest wall, I can see the right lung, I can see the left lung, I can see the cardiac, anatomy, I can see the aorta, posteriorly I can see the vertebral bodies, right? So what is this image actually showing you? This image is actually showing you the internal structure of the patient's body, isn't it? But from what data have I reconstructed this internal structure? I have got this internal structure from the n number of projections of the patient's body, isn't it? So data from n number of projections is used to show or display the internal structure of the patient's body. So what is the basic principle of CT scan? Do you remember? The basic principle of CT scan is that the internal structure of an object can be reconstructed from multiple projections of that particular object. Now, does it make sense to you? Yes, this is how CT scan actually works. Now, over the past many years, there have been several developments in the technology of the CT scan machine. Let us quickly look at, therefore, what are the various CT scan generations. This is the first generation CT scanner machine. It is also called as translate rotate scanner. This was the machine which was first invented by Sir Godfrey Hounsfield. How does it work? See, it has an X-ray tube and a single detector on the other side, diametrically opposite side. Look at the X-ray beam which is produced from this X-ray tube. It is a simple, linear, thin, pencil-shaped X-ray beam, right? That is a peculiar feature of first generation, CT scanner. Now tell me, using such a thin pencil-shaped X-ray beam, how will I be able to cover the entire cross-section of the patient's body? Yes, for that, we'll have to swipe this pencil beam entirely across the patient's body from one side to the other. Can you see that? So when you completely move the X-ray beam from one side of the patient's body to the other, this horizontal movement is called as translation. One translation completely across the patient's body is going to give you one projection. How many projections do we want? N number of projections. So what is done? After one translation is completed, the entire setup is rotated by a small angle, that is rotation. Again, you are at a new position. You again translate, you get projection number 2. You again rotate, then you again translate, you get projection number 3. And that is how alternate translations and rotations are done. Therefore, this machine is called translate rotate scanner. You realize that because of a pencil beam, a lot of translation and rotation is required, and therefore this machine is a relatively slower working machine. Now, just see what is the difference between first generation translate rotate scanner and second generation, which is also called as translate rotate scanner. But look at the animation here. What is the difference? Is it a pencil shaped X-ray beam? No, it is rather a fan shaped X-ray beam which is there. And to detect this, or to collect the information from fan shaped X-ray beam, instead of a single detector, there is a single row of detectors which is used. Otherwise, the functioning is exactly similar. It has to translate from one side to the other, then rotate, then again translate, then again rotate. But because it is a fan-shaped X-ray beam, the degree of translation which is required is less. So this is a slightly faster working machine. Now see here, if you have a fan-shaped X-ray beam which is so wide that it is covering the entire patient's cross-section, right? Do you need to translate the entire setup now? No, right? And therefore, this type of CT scan machine, translation is eliminated. This is called third generation CT or rotate scanner. See why it is called rotate? Because now translation is eliminated, right? The wide fan shaped X-ray beam is covering the entire cross section. So we want to get multiple projections. How are they obtained? They are obtained by rotating the X-ray tube as well as the detectors completely around the patient's body. So there are two structures which are rotating. One is the X-ray tube, the other is the detector, to get n number of projections, and therefore it is called rotate scanner. The problem with rotate scanner is that the detectors, which are electronic detectors, are very delicate structures. So if you rotate them round and round and round and round, they will malfunction. You'll have to replace them. Therefore, detector instability was a significant problem with third generation scanners. Can we eliminate the rotation of detectors entirely so that they would remain stable for a long time? Yes, it was made possible by the development of the fourth generation CT scanner, which is called rotate fixed scanner. See, one rotation of the detectors they have eliminated. But how? See how beautifully they did it. See how simple the concept is. Here in this machine, around the patient, there is a complete 360-degree ring of detectors everywhere around the patient's body. So the only one component of the X-ray tube is now rotating, and of the CT scan machine component is rotating, and that is the X-ray tube. So look at the animation. The X-ray tube is rotating round and round around the patient's body, but a complete 360-degree detector ring is absolutely stationary. Hence the name is rotate fixed. This is an even more faster working machine. Right? Let us quickly revise. See, first generation we started with a pencil shaped X-ray beam, translate, rotate. Then we had a fan shaped X-ray beam, it was still translate, rotate. Second generation, then we used a very wide fan shaped X-ray beam, translation was eliminated, it became rotate. But then detector instability was a problem, so we eliminated one rotation of the detectors. So what do we have? Fourth generation, rotate fixed. So logically, what should be the next generation? It should be fixed. Nothing is moving at all. Is it possible? Yes, nothing is impossible, remember. And scientists have actually come up with a fifth generation CT scanner, and that is what is called as the electron beam scanner. There is not even a single moving part in this machine. See, what happens is that on one side of this particular machine, there is an electron gun or an electron emitter. This is going to emit a high velocity stream of electrons. It is going to pass through certain coils, which are going to be the electron directing or deflecting coils. Now around the patient's body, everywhere around the patient's body, 360 degrees, there is a ring of tungsten. So there is a tungsten target ring which is placed. Do you remember X-ray production we have studied? How are X-rays produced? We have seen in the animation. X-rays are produced when a high velocity stream of electron comes and hits a target anode, which is a heavy metal target. So similarly here, look in this animation, when this high velocity stream of electron passes through these coils, it is directed such that it hits the tungsten target ring. What will happen? When a high velocity stream of electron hits a tungsten target ring, X-rays will be produced. These X-rays will pass through the patient's body. It will be detected by the detectors. There is no moving component in this entire machine at all. This is one of the fastest CT scan machine technology which has been developed. However, it is still in the experimental stages for cardiac imaging, because the heart is beating. We need a very fast imaging modality. That is where its use is being explored. Now, so we have seen 5 generations. There is another problem with certain CT scan machines, and therefore a new technology was introduced, that is called helical CT or spiral CT. What is this? Now just imagine, there is a peculiar problem with usually the third or fourth generation CT scanners. What is that? We know in rotate or rotate fixed that the X-ray tube has to rotate round and round and round around the patient's body, isn't it? But the X-ray tube has very high voltage cables attached to it. What will happen if an X-ray tube to which high voltage cables are attached, if it rotates round and round and round, beyond a few rotations, what will happen to these wires? These high voltage wires will get entangled, they will be pulled out, there will be a short circuit, and the entire machine will explode. We don't want this to happen. So what happened in the olden days was, there was only one rotation of the on X-ray tube which was possible. X-ray tube is switched on, rotated for 360-degree, wires are getting stretched, stop the X-ray tube, switched off, rotated back in a reverse manner, comes back to its original position. That is how one slice image is acquired. Now I want to take the next slice. So what is done? The table is moved inside, so that the next anatomic slice of the body, patient's body, comes at the level of the X-ray tube. Again tube is switched on, one rotation, switched off, brought back to its original position. Second slice, again the table is moved. So this process is repeated such that a slice by slice acquisition of the patient's body is done. But a lot of time is being wasted, isn't it? We wanted a technology which would enable the X-ray tube to rotate round and round and round around the patient's body continuously without the fear of the wires getting pulled or stretched. This was made possible by the introduction of a technology which is called as slip ring technology. Look at the name. There are two rings that are going to slip over one another. So how does it work? See, there is an outer ring, right? There is an outer ring which is completely stationary, and all high voltage cables are attached to the outer ring, right? It is not going to move, so no tension at all, no short circuit or stretching of wires. The inner ring is the mobile ring, right? On this, the X-ray tube is mounted, so it can freely move. No wires are attached to it, right? So it can rotate freely. But how does it receive the electrical supply? The electrical supply to the X-ray tube or the inner ring comes from specific brush contactors. Can you see them here? These brush contactors, they are fixed to this inner ring. Their outer end is free. They are just maintaining physical contact, electrical contact with the outer ring. And that is how the inner ring with the X-ray tube mounted on it is free of any wired attachments. So therefore, it can rotate around the patient's body continuously without the fear of these wires getting stretched out or pulled or there being a short circuit. Now just see, imagine the table on which the patient is lying is moving inside the machine. At the same time, the X-ray tube is also rotating around the patient's body. So if you take both these motions together, it appears as if the tube is tracing the path of a spiral or a helix around the patient's body, and therefore this is called as spiral CT or helical CT. Do you get this? One more advancement about CT scan I want you to know, and that is what is called as multi-detector CT. What is the most important difference between a routine CT and multi-detector CT? See here, a routine CT equipment usually, I said, uses a fan-shaped X-ray beam. If you look at a fan-shaped X-ray beam, it looks like this from the front, but from the sides it is very thin. So look at the image here. When a fan-shaped X-ray beam cuts across the patient's body, it is going to cut through a single slice of the patient's body. But as against that, when a cone-shaped X-ray beam, which is used in multi-detector CT, it has a third dimension along the long axis of the patient's body. So when a cone-shaped X-ray beam is used, when it cuts across the patient's body, in one cut, it is going to acquire multiple slices of the patient's body. As this third dimension of the cone keeps on increasing, multiple slices can be acquired. So it can be an 8-slice multi-detector CT, or it could be 16 slice, or it could be 64 slice, or it could be 128 slice multi-detector CT, in which in one cut across the patient's body, 128 slices of the patient's body are obtained. See how fast this particular machine is, right? Therefore, most of the machines that we use in our hospitals today are at least, 8 slice or 64 slice or at least 128 slice CT scanner machines. They are extremely fast. So we have seen by use of these animations how the CT scan technology has evolved from a first generation translate rotate to a fourth generation or an electron beam scanner. We have seen what is a spiral CT or helical CT with slip ring technology, and we have seen what is a multi-detector CT which uses a cone beam rather than a fan beam. I hope you have enjoyed the animation and you now know how a CT scan actually works, what happens inside a CT scan machine, right? Now, let us quickly discuss what is this Hounsfield unit scale or CT value scale. Now see, on a CT scan image, each and every tissue in the body is given a numerical value. That value given to that particular tissue, right, is called as its Hounsfield unit value or HU value or CT value. How is it calculated? It is calculated by using this formula. Hounsfield unit value of a particular tissue X is equal to 1000 multiplied by mu of that tissue X minus mu of water divided by mu of water. What is this mu? This mu is a complex entity in CT scan physics. It is called as linear attenuation coefficient. It is called linear attenuation coefficient. This is a complex entity in physics, but it is determined by one particular property of a tissue, and that is its density. So what property of a tissue determines its LAC value or mu? It is its density. Now I want you to apply a little bit of mathematics, right? Just look at this. equation. Tell me, using this equation here, right? Tell me what will be the Hounsfield unit value of water. Look at the equation. So X will become water. So what will be Hounsfield unit value of water? 1000 multiplied by mu of water minus mu of water divided by mu of water. So numerator will be 0. Multiplied divided by anything, answer will be 0. So therefore, if this is the Hounsfield unit scale that I have drawn, at the center point of the scale at 0 HU, you have water. Remember, this is the positive side of the scale on this side, where all the tissues which are denser than water will lie on the positive side. This is the negative side, where all the tissues which are less dense than water will lie on the negative side. On the positive most, or on the, let us start from the negative most extreme. On the negative most extreme lies the least dense tissue in the body. What is that? It is air. It has a Hounsfield unit value of minus 1000 HU. Next to air is an organ in the body which is predominantly composed of air. What is that? It is lungs. Minus 800 HU. On the negative side, there is another important tissue, and that is less dense than water. That is fat. It has a value of minus 100 HU. Now, on the positive most extreme lies the most dense component in the body, that is bone. It has a value of plus 1000 HU. Almost all the soft tissues in the body lie in between water and bone. It is impossible, impractical to remember the Hounsfield unit values of each and every one of them. We'll remember the value of a few important ones. One important one I want you to remember is acute hemorrhage. And this acute hemorrhage has a Hounsfield unit value of plus 45 to 65 HU. So just imagine, on a CT image, you see any abnormality, you put a measurement pointer there. Just by looking at that numerical value at that point, you'll be able to see what tissue lies there based on its density, right? Let us apply this. This was the quiz question that we started with, right? So see here, whatever history, clinical examination, whatever they have given, right? We are least concerned with it for 1 minute, say. For example, I put a measurement pointer over here, and this measurement pointer tells me that the HU value at this point is plus 55 HU. Can you tell me plus 55 HU is what tissue? Let us go back to the Hounsfield unit scale. See, plus 55 HU lies in this range. So what is this? This is acute hemorrhage. So what is your diagnosis here? Your diagnosis here is going to be an intraparenchymal bleed, because this is bleeding inside the parenchyma. This cannot be an extradural hematoma. This cannot be a multiple sclerosis. This cannot be an infarct. Right? We'll discuss in neuroimaging in detail why this is an intraparenchymal bleed, why this is a hypertensive bleed. Look at the blood pressure. What is the most common site of hypertensive bleed? Everything we'll discuss. But irrespective of knowing all these things, just by knowing at the Hounsfield unit value, we can get a correct diagnosis. That is the great utility of the Hounsfield unit scale. Right? Walls of a CT scanner room are lined with what? We just discussed. They are lined with lead. And what is the purpose of using lead? Right, the purpose of using lead is to prevent the leakage of radiation from occurring from the CT equipment room to the outside. Now that we have studied the basics of CT scan as a modality, as we go ahead, we are going to discuss how to interpret CT scan images, and we are also going to discuss it in detail in the neuroimaging part when we look at various abnormalities in the brain.